today we're going to be using Green's theorem to find the value of this line integral. So use Green's theorem to find line integral xy squared dx plus 3xy dy, where c is the curve that bounds the region, bounded by y equals root x, y equals x squared in the first quadrant, with c is oriented counterclockwise. Yeah, this is a multivariable calculus problem here. So let me go ahead and look at Green's theorem first of all, which says that the line integral of c p dx plus q dy is equal to the double integral over the region R of change in q, change in x, minus change in p, change in y, dA. Where c, this is important, is a simple closed curve oriented that if you're walking on c, the region is on your left. A couple things. Simple closed curve, mainly the simple part is basically that's the curve is not going to intersect itself, again, is what we're saying. And when we're talking about the orientation here and the walking part, the idea is this theorem holds if the orientation of the curve is such that if you're, imagine like walking on it, that's on the curve, the region that you're speaking of is to the left of you, okay? That's when this theorem holds. Now, not a big deal if you were to go in the other direction, meaning that, let's say, if you were walking, the region would be on your right, let's say, instead. So it's like you're going like clockwise, even that way. That's not a big deal. You would just basically negate that result. And I'm mentioning that because when you're doing a line integral technically has a direction to it, and the direction can be affected by a plus or minus. So that's why this has to be mentioned here. And this is the result is for an orientation where the region again is on the left of the curve. Okay, so we have the conditions met. This is a simple closed curve. It's made up of y equals root x and y equals x squared. It's a combination, but that's fine. And the way this works is if you use Green's theorem, you're going to start out with picking what p is and what q is. So p is just what's in front of the dx, and q is what's in front of the dy. And you're going to go ahead and take change in p, change in y is 3xy. Change in q, change in x is 3y. So just following the formula up here. And you're going to subtract those two from each other. And you get 3y minus 2xy. So let me concentrate over here. Zoom in on that. And you're going to set up basically a double integral over that region. So it's like an area, okay? And you would go ahead and apply all the techniques you've learned about setting up a double integral. It's nothing different there. And I went with the order dy dx. It's up to you to pick which one you want to work with here, the order, if it applies. And so this region is bounded between square root of x and x squared. And your x's go from 0 to 1. Okay, so that is, that's why that setup is true. We go ahead and integrate, and I'll leave you to that, but these are the details here. And that comes out to be 17 over 60. And that's our result. Now, if you hadn't done Green's theorem, applied Green's theorem to figure out the value of this line integral, you would have to go ahead and parametrize two curves. You'd have to parametrize x squared and then the square root of x. Okay, and that's what C1 stands for. It's the parameters is basically the x squared, and C2 stands for the square root of x. So you have to do two line integrals here because those two curves have different parameterizations. I parameterize C1, which is the parabola. T squared is a parameterization for that from 0 to 1, and then your r prime is 1 dt, or your dx is 1, and your dy is 2 dt. We prefer to write it out that way. Similarly for R2 would be 1 minus t, square root of 1 minus t, because you're going from the point 1, 1, which should be like right here, down to the point 0, 0. So that's why I have to plug in that 1 minus t to take into account for that. And similarly, I figured out r prime, got my dx and my dy, and you plug that information in for each of these line integrals. So that's my value for C1. And then similarly did that for C2. And yeah, a lot of algebra here that you needed to do. And then you would add the results, or in this case subtract because one is negative. And your answer would come out to be the same thing, 17/60. Okay, so that's the advantage of working with Green's theorem, is that it can cut down on your computations with a line and a rule. Okay, so thank you so much for your time. Hope this helps.